Our planet was born in fire, then grew with disaster. Yet even then, the elements of life were present. Water was soon present on the surface. When calm, it would provide a sheltered cradle for the first life on Earth. While the planet was born in fire, it was baptized by ice. For millions of years, it was covered by a frozen shroud. Yet it seems that life not only persevered, but prospered. Microbes evolved into a myriad creatures, and one was the first to leave the oceans forever and tread on land. Only a few million years ago, creatures that we most resemble began to walk the earth. Our own lives seem so fragile, yet science tells us otherwise. It tells us that we are but a part of the greatest journey ever made. It tells us that all life is linked through time to those simple cells which drifted once in the first oceans of a miracle planet. Four and a half billion years ago, the Earth was a very different world. Under layers of thick gaseous clouds was a planet still hot from its birth, with an atmosphere both dense and crushing. Bathed in filtered red light were oceans far deeper than those of today. And there was one other great difference. The early planet was probably only a tenth of the size that it is today. But it was to grow. And that chance and violent growth would prove crucial to life's history and to what we are today. The early solar system was far more crowded than now. Where today the four inner planets orbit, 4.5 billion years ago were scores of smaller planets orbiting the sun. Orbits of some were drawn by gravitational force towards each other. Encounters of awesome magnitude were unavoidable. The force and heat of those collisions melted the rock, but gravity would hold the two together and then weld them into one. With each collision, the planet would grow larger. We believe that of the four innermost planets, Mercury was formed by only one or two such collisions, while Venus, almost the size of Earth, was formed by 8. Mars may have escaped any collisions. But Earth grew largest, perhaps from as many as 10 impacts. And the last impact, 4.5 billion years ago, would have a profound effect upon our world. The giant body crashed into the center of the planet and gave Earth its iron core. The lighter debris was cast off into space and then drawn into orbit around the enlarged planet. For some millions of years, the Earth had rings like the planet Saturn. Smaller collisions continued, and from that debris was born our moon. It was chance and chance alone which made our planet larger than any of the other planets close to the sun. And somehow, somewhere in this chaos, life began. But quite where is open to conjecture and debate.
First life probably emerged on the Earth by 4.4 billion years ago, fairly soon after the Earth formed. My guess would be that this life came from Mars. Mars was open for habitation before the Earth is. It's a much safer place to live if you're a microbe early in the solar system. If life evolved on Mars, rocks would get knocked off and this would seed the Earth.
Could life have formed on Mars? We know because of the evidence of erosion that water once flowed freely on the surface, that Mars did indeed have an atmosphere, that conditions were suitable to sustain early primitive life. But Mars is a small planet with weak gravity. Over time, the atmosphere escaped into space. Most of the water vanished too, either into space or held deep in the ground as permafrost. We know, too, that Earth has been hit by rocks that originated from Mars. Some scientists are positive that primitive microbial life could withstand that journey. But the Earth, because of its size, had enough gravity to keep its oceans. Over the ages, continents have shifted their positions, wind and rain shaping and reshaping the surface. Ice has scraped its way across the face of the land, and the seas have risen and fallen again and again over time. Here, in Greenland, are some of the oldest exposed rocks ever to have been found. And one belt of rock, 4 kilometers, almost 2 miles long, may take us back as far as we can go in the long history of this planet's existence. Dr. Minnick Rosing of the Geological Museum of Copenhagen has visited Greenland many times in his research for evidence of Earth's early history. And close to the margin of the glaciers, at a place called Isua, he has found one of the oldest rock beds on the face of the planet. Here is the geological evidence that this was once an ancient seabed. This rock was once molten lava, which flowed 3.8 billion years ago. Its shape and structure identify it as pillow lava, which can only form underwater.
Pillow lavas show you that there was oceans or that there was water on the surface of Earth 3.8 billion years ago. And we know on the ocean floor today that this is the habitat of many life forms. And this could be a place where life emerged on Earth in such environments. And this is a very rare thing. We have been walking now for a couple of hours through rocks where you can't see anything, and then suddenly there's like 1 square meter where you can look 3.8 billion years back in time and see what happened on Earth at that time. So there are a few very rare glimpses where you can look way back to the most distant parts of Earth's history.
But there is another rock, unremarkable to look at, which hints that life might also have been present. Only a meter or so square, no larger than a beach towel. It too is 3.8 billion years old. This rock was also part of an ancient seabed, but it is the black band which fascinates Minnick Rosing. This is a layer of fossilized carbon which he believes might be the earliest evidence of life. Under the microscope, tiny black grains can be seen. These possibly are grains of carbon, the building blocks of life. If so, there may have been tiny microorganisms drifting in the water that were alive, taking in nutrients, reproducing, and then dying and dropping slowly to the ocean floor. When the carbon was deposited those billions of years ago, the thin straight lines on the rock show it was undisturbed, proof that this was the bottom of a deep ocean, and the thickness indicates that already life was plentiful.
This is not the emergence of life. It cannot be, because we have all this black color, and that means that there was very efficient life that could make a lot of carbon, and this life must have been very sophisticated. So life must have been had a long prehistory, and one could speculate that probably life formed on Earth maybe 4.3 billion years ago, when the oceans formed and the conditions for life were present. Life could have emerged at that time, and definitely by 3.8 billion years ago, life had reached a level of sophistication that allowed it to live in the water and produce a lot of carbon. So it was highly advanced life at this time.
For these microorganisms, the prerogative was simply to survive. But the challenges to life were daunting. The early solar system was still a violent place. Asteroids come hurtling out of space, attracted by the greater size of the planet. And on the face of the Earth today, we can see the scars of recent collisions. This crater in Arizona is well known. It's the Barringer meteorite crater and was gouged from the surface only 50,000 years ago. The impact crater is huge, 1.2 kilometers across, just under a mile, and it was thought that the size of the meteor must have been the same. So perhaps buried in the ground was a fortune in iron and nickel. In the early 1900s, the Standard Iron Company was formed by Daniel Barringer to dig out the perceived wealth.
When my grandfather came up this ridge and looked at it, he imagined that the object that made this hole was at least as big as the bottom diameter of the crater, which is, again, more than half a kilometer. He thought this would be millions and millions of tons of nickel iron, and it would be commercially immensely valuable, that he could make millions of dollars here.
The mining venture lasted 27 years, and in today's money cost around $10 million. But nothing of any value was found. But while the mining venture gained nothing except a useless shaft,
Ready? There it goes.
there was to be a winner after all. It was science. In 1928, a paper was published which concluded that the mass of the meteor was far smaller than the size of the crater. Further mining was called off, and shortly after, Daniel Barringer died of a heart attack.
I think I could have easily made the same mistake because it's such a large hole, and it's intuitively, it seems like it would have had to be a huge rock that would have made it.
In fact, the meteorite which caused this crater was no larger than the perimeter fence around the mine shaft. Science learned it was the force that was as critical as the size of the object. But about 4 billion years ago, the Earth was hit by a massive space intruder, 10,000 times larger and 1 trillion times heavier than the rock which grazed the Earth in Arizona. At Stanford University in the United States, Dr. Kevin Zanley of NASA and Dr. Norman Sleep from the university are studying the impacts of meteorites on Earth. But first, they must look at the moon.
But you like to look at it pretty early, so you get nice shadows. It's also pretty nice to start with.
On the Earth, the evidence of the very earliest asteroid strikes have been weathered away by erosion or lost with the tectonic movements of the Earth's crust.
Globe. Let's see if we can orient it the same way. Whoa, where is everything?
But the moon has been stable since its creation over 4 billion years ago, so craters are there from that long distant past. By looking at these craters, they hope to estimate the number of times the early Earth might have been hit. It is far larger, its gravitational attraction far stronger, and they estimate that our planet was hit 25 times more often.
Nobody is steering the asteroids that are going to hit, and the Earth, being bigger, just happens to get hit more often.
So what we do is we count the big craters on the moon, and then we scale up to the much larger size of the Earth, and we find that the Earth was hit by asteroids as large as 500 kilometers across, at the same time that the moon was being hit by asteroids that are 100 or 200 kilometers across.
This is an impression of the relative sizes. The largest is 500 kilometers. That's over 300 miles across. Earth may have been hit as many as 6 times by an asteroid this size.
You have a 500-kilometer object moving at 20 kilometers a second, stopping in 20 seconds, delivering all of its energy in doing so, and you produce an enormous explosion. The amount of energy that is released in this event is more than enough to evaporate the world's oceans.
A massive asteroid from outer space heads straight for Earth. It's as large as the one that impacted over 4 billion years ago. This computer simulation has been made with the scientific advice of geophysical experts to show the effects if the impact were to happen today. The asteroid's diameter is larger than the main island of Japan. Even though it is moving at over 720,000 kilometers an hour, that's almost 450,000 miles an hour, the asteroid appears eerily slow because of its size. The actual impact happens in the Pacific Ocean, just under 1,000 miles south of Japan. The crust of the Earth is peeled away like an orange skin by what is called the crest tsunami. Even the deepest part of the Pacific Ocean looks like a thin film. Huge chunks of debris the size of city blocks are hurled into the air. The entire Japanese archipelago is disintegrated, as is some of the Asian continent. The shattered remains are hurled out into space way beyond the atmosphere to bombard the Earth with deadly intent when they re-enter. At 7,000 meters, 23,000 feet, the rim of the crater is higher than many mountains on Earth today. The size of the crater would be a distance of 2,500 miles or 4,000 kilometers. And this is just the start. NASA has the world's largest collision test machine used to try and find out what would happen after the moment of impact.
Okay.
Dr. Peter Schultz fills a small tank with water to see how the ocean would react. The actual impact object is tiny, but it will hit the water at a speed 20 times faster than a bullet fired from a pistol.
Oh, gorgeous. Joe, that is gorgeous.
Just one tiny aluminum bullet had this result. But the impact which created mayhem is not the entire story. To get the full picture, the moment of impact has been slowed down so that 1 second seems to last an eternity. At the moment of impact, it is like slamming the brakes on. The kinetic energy of the bullet is transformed into heat. White smoke rises. It may look like a splash, but it is actually water vapor. The heat vaporizes the water in an instant. And heat has a deadly potential.
When an asteroid hits the surface of the Earth, the material is heated up to temperatures that get up to the point of, say, 4,000 to 6,000 degrees centigrade. This is as hot as the surface of the sun.
An experiment was carried out at Hokkaido University in northern Japan to try and discover what could happen to the rock bed at the point of impact. A tiny rock was put into a special oven that could cook the sample to a temperature of over 2,000 Celsius, 3,600 Fahrenheit. As the temperature rose higher, the rock began to melt and boil like water. The gas produced is called rock vapor.
The rock vapor, when we generate this rock vapor, it will expand extremely fast. It expands so quickly that it can cover eventually the entire planet. When an impact hits, it's not just the crater that forms, it's not just the area where the impact occurred. It's all the heating that's created in the atmosphere and around it. So heat really is the killer.
Moments after the impact, rock vapor, the temperature of the sun, begins to engulf the world. Could any life at all survive this impact? Immediately after the impact, the rock vapor rises up from the crater in a dome, then spreads out in all directions across the globe. 3 hours after the impact south of Japan, the expanding wall of vaporized rock reaches the mountains of the Himalayas. The perpetual snows are instantly evaporated. Soon the wall of fire reaches the Amazon, the furthest distance from the point of impact. The forest spontaneously combusts even before the rock vapor arrives. Just 1 day after the impact, the entire planet is covered. Every living plant or creature is vaporized. It's been estimated that this vapor would cover the entire globe for almost a year. It would be as if the sun had come to Earth. The ocean would start to bubble and boil. And as the water evaporates, the oceans would drop at the rate of 5 centimeters or 2 inches every second. Even the salt deposited on the ocean floor vaporizes, and then the very bottom of the sea melts. Nothing is left untouched. One month after the impact, the surface of the world has been sterilized. The oceans have vanished. All that remains is the superheated bedrock. It is thought that an impact like this happened 6 times in the violent past of the Earth's history. If there was life, it was assumed that it too would have been wiped out, only to begin again. But now science is not so certain. Now there is the strong likelihood that life, despite the odds, has survived. But how could that be possible? With the oceans gone, where could life have found a sanctuary from the searing heat? A clue to the answer was found in salt. These salt lakes in the American Southwest are the remnants of an ancient sea. Millions of years ago, in the Permian era, the upheaval of the bedrock drained the oceans and left behind these lakes. Dr. Russell Vreeland is a microbiologist based at Westchester University. He's been studying the survival strategies of microbes and has come up with some remarkable results. His study site is a repository for nuclear waste located beside one of the lakes. The waste site is right in the middle of nearly half a mile of rock salt. Over time, this salt gradually expands, which is why it makes a good storage medium. But if nuclear waste can be locked out, traces of ancient microorganisms could be locked in. The salt crystals within these walls have lain untouched and uncontaminated since the ocean dried out millions of years before.
Find some areas with the pipe. Here's one here, yeah. With the...
And inside the crystals, Dr. Vreeland thought he might find traces of the microbes that lived in that long-dead ocean.
Very good example, actually, in my opinion, because we have very nice defined bands and striations. We have, and each of those represents a tiny, tiny droplet of the Permian Ocean that was trapped and has been held in that crystal for 200 million years.
To him, these crystals are as valuable as any gemstone. Inside the crystal are minute droplets of the seawater trapped within as the salt crystallized. A tiny hole was drilled so that the drop of water could be released. Perfectly shaped microorganisms named Bacillus permians were found, relics from the past. But the next finding was truly extraordinary. For 4 months, the microbes were fed with a nutrient broth. They began to divide, then multiply vigorously. After slumbering through tens of millions of years, they had come awake.
Bacterium that we found in the crystal was neither alive nor dead. It was in a state of long-term suspended animation. As a spore it just literally could do nothing but sit and wait. Amazing part about a dormancy like that is that they don't need nutrients, they don't produce waste product, and they have the ability to just sit and wait until conditions are favorable again for survival.
Yet it seems that life did exactly that. It survived.
I find amazing is life is really tenacious. And once it came about, once it evolved, once it was on this planet, it would have taken a huge event to sterilize the planet. You would have had to heat the planet literally all over, and as deep as you possibly could, virtually melt the planet to really destroy the life.
To survive millions of years trapped in salt looks easy compared to the virtual end of the world.
When you have an impact, you have that instant in which all this energy is converted to heat. But that's only part of it. You then have the vapor that expands and heats up the atmosphere as well. So now you are no longer dealing with just the point of impact and the vapor that's created there. You now have material that's expanding. Eventually, some of that material is expanding and goes out of the atmosphere of the Earth, then comes back down. During the time when it comes back down, it's generating more radiation, so that you have the heat of the impact, then you have the material, the vapor that heats the atmosphere, then you have ejecta that returns to the surface of the Earth. And as it goes through the atmosphere, it will create enough energy to literally fry, completely combust any living organism that would exist.
The total evaporation event that occurred around 4 billion years ago was catastrophic. Water as well as salt deposited on the ocean floor evaporated. There are microbes that actually like heat, but not heat like this.
It is going to be rich, though.
Dr. Sleep of Stanford University looked long and hard at early life's survival capabilities. He thinks that he's found an answer. There was a part of the Earth where life could sustain itself, and this was deep below the ocean floor. This graph shows the temperature distribution in the subsurface of the Earth. The red area is the heat from the Earth's core. Nothing can survive in this region. Green are regions below boiling point. Blue are regions just below 50 degrees Celsius or 122 Fahrenheit. Life could survive in the blue zone, the Goldilocks zone, as Dr. Sleep calls it. It has been estimated that the temperatures on the surface of the Earth would have reached as high as 2,000 degrees Celsius, over 3,500 Fahrenheit. What the researchers wanted to know was how deep would the heat penetrate and how fast could it travel down into the Earth? Would the heat from above meet the heat from below? The heat from above travels slowly and steadily, about 1 meter or 3 feet every year. The simulation showed that there will always be regions where life could survive.
Any organisms that are living deep underground, like 1 to 2 kilometers thick, will be fairly safe. The heat pulse doesn't last long enough for the heat to propagate down to that depth. It's a little like when you cook a turkey. You can't cook a turkey in your oven in 1 minute. If you try to do that, even if you get the outside very hot, the inside will still be cool. We have the temperatures here At the ridge axis, things are relatively hot. As we get away from the ridge axis, it's relatively cool. An ordinary organism, you want to be here in the blue.
If life were present 3.8 billion years ago, then the life that we have on Earth now would have descended from life that liked higher temperatures, or was more able to survive high temperature waters, and was not photosynthetic.
However, early life needed water, and the water on the surface of the planet was gone. Was it possible to sustain any sort of life in the rocks deep below the Earth's surface? Here in South Africa, that question has been answered. Gold brings wealth to a country, but the job of getting that gold is dangerous. This is one of the deepest man-made shafts in the world. It drops down over 2 miles below the surface. And it's not just the miners who take the long trip below.
Luckily, Lawrence Rob from Wetskyn.
Dr. Esther van Heerden of South Africa's Free State University is researching the survival of life deep within the Earth. Her findings and those of the research team are astounding. Before these shafts were excavated, there was nowhere for scientists to search. It's dangerous down here. For every half-mile underground, the temperature goes up by 10 to 15 degrees. And there is the constant danger from methane. High levels of this gas would cause an explosion, so it's frequently monitored. Even so, methane is constantly leaking from the rocks. Yet life actually was found here. Groundwater is seeping from the rocks, and the surface of the mine wall is covered by a thick film of white and black. This is a mat of various forms of bacteria, species not found on the Earth's surface. Here they do not use oxygen, they are anaerobic. But research shows that many of them still possess the genes for oxygen respiration, useless down here. Perhaps this is evidence that these microorganisms once lived on the surface, only to migrate to these depths, perhaps to escape the heat of a total evaporation impact.
Initially, we thought that life only existed 2 feet from the surface. We now know that through access through this deep mine subsurface project, that there are organisms as far as 3 kilometers underground. Had we had access to other deep subsurface environments, surely we might find traces of organisms there, which might indicate the same pattern as we are seeing here.
This deep underground world has been a refuge for life for possibly billions of years. So far as we know, when life first formed on the planet, it lived in the oceans. It spread out, and some life forms clearly moved down into the dark subsurface of the Earth to quietly remain in cracks and in rocks, residing in waters heated by the Earth's inner mantle.
If we look at these organisms living in these environments, they have adapted to survive. Their main aim is just to survive and sustain themselves. Surely, as things change, new organisms, all these organisms will change and adapt to make sure that life is sustained on the planet no matter what happens.
To survive is life's objective. And sometime after the total evaporation event, life must have once again returned to the surface. Immediately after the impact, the planet would have looked like a fireball. But within only a year, the rock vapor would start to dissipate and temperatures would begin to drop. Because of the Earth's size and gravity, the evaporated water would not escape into space, and within only 1,000 years, the water vapor would cool and condense, and then fall back as torrential rain. Once again, the oceans would start to fill. The rainfall would be as heavy as tropical rain is today, and in only 3,000 years, the oceans would have regained their original depth. The stage was set for life to return from the deep.
There's always likely to be some area deep in the subsurface of the Earth where the heat pulse does not reach. It's probably an area that's fairly deep, so the organisms that are living there are high-temperature organisms to begin with. These would be the organisms that survived, and these are probably our ancestors and the ancestors of all the other life on the Earth.
Those early ancestors of life on this planet had endured against all odds. They had survived searing heat to once again recolonize the oceans. From deep within the world, from minute cracks and fissures in the bedrock, the underground life returned to the surface. Perhaps one day in the far distant future, life may once again be forced to revisit those depths. How many times this has happened, we perhaps will never know. For the next 2 billion years, life remained in the oceans of the world, drifting in the waters, taking nutrients, reproducing, and dying and living. The next challenge to life came almost 2 billion years ago. And if science is correct, it came not with a mighty impact, but slowly and insidiously. For millions of years at a time, the planet was shrouded with a thick covering of ice. Life endured that too, but how? That answer is locked within the history and the science of the only world we know.